Continuation. So we're now going to discuss LU decomposition. So Gauss elimination is designed to solve systems of linear algebraic equations of a matrix form AX is equals to B. Although it certainly represents a sound way to solve such systems, it becomes inefficient when solving equation with the same coefficient of matrix A but with different right-hand side B. So recall, the Gauss elimination involves two steps, forward elimination and the back substitution. Of this, the forward elimination step comprises the bulk of the computational effort. This is particularly true for large systems of equations. So LU decomposition separates the time-consuming elimination of the matrix A from the manipulation of the right-hand side B. Thus, once coefficient of matrix A has been decomposed, multiple right-hand side vectors can be evaluated in an efficient manner. Interestingly, Gauss elimination itself can be expressed as LU decomposition. LU decomposition requires pivoting to avoid division by zero. However, to simplify the following description, we will defer the issue of pivoting until after the fundamental approach is elaborated. In addition, the following explanation is limited to a set of three simultaneous equations. The result can be directly extended to n-dimensional system. The equation above can be arranged to give a coefficient matrix A and the variable x minus b is equals to 0. Suppose that this equation could be expressed as an upper triangulation system. Recognize that this is similar to the manipulation that occurs in the first step of Gauss elimination. That is, elimination is used to reduce the system to upper triangular form. It can also be expressed in matrix notation and rearranged to give. Now assume that there is a lower diagonal matrix with ones on the diagonal that has the property that when is pre-multiplied, the result is, if this equation holds, it follows from the rules for matrix multiplication that LU is equals to A and LD is equals to B. So a two-step strategy, as shown in figure 10.1 for obtaining solutions, can be based on the following equation. First is LU decomposition step. A is factored or decomposed into lower and upper triangular matrices. And two substitution steps. So the lower and upper are used to determine a solution X for the right hand side B. This step itself consists of two steps. The first equation is used to generate by forward substitution. Then the result is substituted into the upper, which can be solved by back substitution for x. On the decomposition, so we have here the given matrix, the variable in the right hand side. We have here the upper and lower. First, we need to apply, so forward. So we have the lower multiplied by the intermediate vector and equals to B and move here. So we will use the D here and we'll now be using the upper and X and we'll be able to find the value of X. So in order for us to understand more this particular figure or process, so we will have an example later on. So continuing the discussion, so we have here the LU decomposition with Gauss elimination or Doolittle decomposition. Gauss elimination can be used to decompose the matrix A into the lower and upper triangular form. Recall that the forward elimination step is intended to reduce the original coefficient matrix A to the form of matrix A and the lower matrix, and for the upper, so these are the representations, which is in the desired upper triangle format. Although it might appear at face value to be unrelated to LU decomposition, Gauss elimination can be used to decompose A into lower and upper triangle format. This can be easily seen for upper, which is direct product of the forward elimination. Recall that forward elimination step is intended to reduce the original coefficient matrix to the form. So the first step in Gauss elimination is to multiply row 1 by the factor and subtract the result from the row 2 to eliminate A2-1. Similarly, row 1 is multiplied and the result subtracted from the third row to eliminate A3-1. The final step is to multiply and modify the second row by the factor 3 sub 2 and subtract the result from the row to eliminate A prime 3, 2. Where do we store the factors 2, 1, 3, 1, and 3, 2? So recall that the whole idea behind the elimination was to create zeros in A21, A31, and A3. Thus, we can store F21 in A21, F31 in A31, and F32 in A32. After elimination, the coefficient matrix A can therefore be written as this particular matrix form. So this matrix in fact represents an efficient storage to the LU decomposition of A. So we have here the coefficient matrix A and change into lower and upper triangle format. So this will be for the upper and this will be for the lower. So the following example confirms that A is equals to lower multiplied by upper. So in order to understand more the given solution process, so let's have an example. So for example, problem statements derive an LU decomposition based on the Gauss elimination performed in the previous example. So we're going to use the same example as we have applied in our Gauss elimination. For the solution, in previous example, we solved the matrix. So we have here coefficient matrix. So after the forward elimination, the following upper triangular was obtained. So you will notice this is what we calculated during our naive Gauss elimination. So this is simply forward elimination. So we have here the elements of the lower triangulation or the lower triangular form is equals to 0. So the factors employed to obtain the upper triangular matrix can be assembled into the lower. So the elements of A21 and A3 were eliminated by using the factors. So you will notice this is part of first modified and during our process of Gauss-Jordan and naive Gauss elimination. And this is part of our second modified or our naive Gauss elimination. And during our Gauss-Jordan, this is part after the normalization of the second equation. So these are the factors used. So in continuation, using the factors, so this is for our lower. So consequently, the LU decomposition is, so it will be represented in this particular representation. So we have here the factors. So these are the two factors. And for the upper, so we used here the forward until forward elimination. So this result can be verified so by performing the multiplication of LU to give. So we have now the value of LU. So 3, 0.099, so on and so forth, where the minor discrepancies are due to round off. So that's what I tell everyone to avoid rounding off or chopping off numbers. So please use the original resulted value as much as possible. So for the substitution step, the problem statement, so complete the problem initiated and do little composition by generating the final solution with forward and back substitution. So given the equation, we are now our substitution step. So as stated above, so the intent of forward substitution is to impose the elimination manipulation that we had formerly applied to coefficient matrix A on the right hand side vector B. So recall that the system solved was in this particular form. So this is the matrix form that the forward elimination phase of conventional Gauss elimination resulted in this particular equation. So you will notice this is part of the forward elimination. So you can recall our naive Gauss elimination. So the forward substitution phase is implemented by applying the equation 10.7 to our problem. This is the representation of L, so multiplied by D equal to the right hand vector of B. So this is the lower triangulation multiplied by D and this is our right hand vector. Or multiplying out the left hand side vector, so we were able to have this particular equation And with this particular equation, so we can now solve for the values of D1, D2, D3. Thus, the values of our D. So, D1, D2, and D3, which will be used as the right-hand side now of the equation. This result, so it will be represented by this particular equation, wherein this is simply the upper triangulation x equated to D. Can be solved by back substitution. We're able to find the values of x. So, in order for us to really understand the step-by-step process, we will try using Excel and apply LU decomposition with Gauss elimination. Using Excel in applying LU decomposition, for example, from the conventional form of equation, so we're now going to represent them into a matrix form, coefficient matrix, the variable x and the right-hand side b. And after that class, using LU decomposition, or the so-called Doolittle's or cross decomposition. So, the process is first make it in this particular form, and second, to represent the matrix coefficients of A into the lower and upper decomposition, or the lower and upper triangular representation. So, first, we have the value of A. So, equate lang natin siya. So, this is the value of our matrix A in order for us to simplify the process and to make it more understandable than what we have discussed on presentation. So, for the lower triangular, the main diagonal with 1 and the upper triangular with 0. So, let's represent these factors here. So, let's say this is A, so this is B, and this is C. So, instead using F sub 2, 1, F sub 3, 1, and F sub 3, 2. And for the upper would be D, E, F, 0, G, H, 0, 0, I. So, for our upper triangular format. So, this is the A11, A12, A13, and this will be A prime sub 22, A prime sub 23, A double prime sub 33. Para mas masimplify yung process, we just use A, B, C, D, E, F, G, H, I. So, this is the LU decomposition. So, this is for matrix A, for our matrix F, for our matrix U. So, next will be matrix A. So, equate lang to. And for the lower and upper, so, we're going to have the product matrix. D will be E. So, F din dito. And so on, apply lang natin yung application ng multiplication of matrix. This will be AD. This will be AE plus G. This will be AF plus H. And this will be BD. This will be BE plus CG. This will be BF plus CH plus I. So, equating them, so we will have here first D is equals to 3. For E equals to negative 0.1. So, let's just equate. So, equate lang natin. 0.1. For F, it will be negative 0.2. So, AD will be A multiplied by the value of D, which is 3. So, this will be equals to 0.10. So, we will be able to find the value of A equals to 0.1 divided by the value of D. And for our AE plus G, so we have the value of A, 1 over 30. So, this is the representation in fractional form of our 0.03333. So, multiplied by the value of E, which is negative 0.1. So, plus G. G is still unknown. AE plus G is equals to 7. And G will be equals to 7. So, 7 minus 1 over 30, the value of A multiplied by E. So, the value is 7.033. So, for AF plus 8, so this would simply be A has a value of 1 over 30 multiplied by F. So, F is negative 0.2. And the value of H is still unknown. But we can equate them to negative 0.3. And the value of H would be negative 0.3 minus the value of A multiplied by the value of f. So we have here the values that will be used later on. So for BD, so BD is equals to, for the value of B is still unknown, so B multiplied by D3, and we all know that BD is equal to 0.3. So we will be able to find the value of B, which is 0.3 divided by 3, and we have here the value 0.1. So for BE plus CG, so this will be, the value of B is 0.1 multiplied by E, the value of E is negative 0.1, plus the value of C, so the C is unknown, and we have the value of G. So the value of G in fractional form is 2101 divided by 300. And we all know that BE plus CG is equals to negative 0.2. So we will be able to find the value of C. The value of C is equals to negative 0.2. So minus, so ilagay natin sa parenthesis, minus the value of B multiplied by the value of E divided by the value of G. So this will be the value of C. Next would be BF plus CA plus I. So we will be able to have the value of B as 0.1. So galing dito. The value of F multiplied by F, which is negative 0.2, plus the value of C. So the fractional value of C is negative 57 divided by 2101 multiplied by the value of H, and the fractional value of H is negative 22 divided by 75 plus I. I is unknown kasi wala pa tayong value. And we can equate this equation. So BF plus CH plus I is simply equals to 10. And we will be able to find the value of I. So I is equals to 10 minus the value of the product B times F minus the product of C times 8. So this will be the value of I. So from here, we will be able to substitute the values of A, B, C, D, E, F, G, H, and I as our lower and upper. So for lower, and this is for upper. So we will have here for the lower, so we have the main diagonals as 1. And for our upper triangulation, so we have zeros. And we have the values at the lower is ABC. So A for B and for C. So this will be the value of lower. And for upper, so we have here DEF, GHI. So we have the lower triangulation as 0. So for D, E, F, and G, H, and this will be for I. So this is the matrix representation of upper. And next, we'll be going to calculate or to find the value of the intermediate vector, so represented as D. So we're going now to find the value of the intermediate vector D using the lower multiplied by D. So D is the intermediate equated to the right-hand side vector B. So for the lower, so simply copy the values for our lower. And for the intermediate, D1, D2, and D3. For the right-hand side vector, so we're going to select our main problem. So from here, we will be able to have an equation represented as this equation, and we will be able to find the value of D1. For D1, the equated 7.85. And for our D2, this is the difference of our product of coefficient matrix multiplied by the resulted D1. So this will be our D sub 2. And for our D sub 3, so the right-hand side vector minus the product of the coefficient matrix of D1 times the value of D1 minus the coefficient matrix of D2 times the value of D2, and we were able to find the value of our D sub 3. And using this, we will now proceed to the next solution process, which is the upper, applying this by the variable x. So we will be able now to find the value of the unknown x. So for our upper, so using the upper data, so copying out this data set, and the x, simply the unknown x sub 1, x sub 2, and x sub 3, and using the calculated intermediate vector D. So, using these values, and we will now be able to generate equation and apply back substitution similar to the Gauss elimination process. So, with this, we will be able to calculate first the value of x sub 3, next x sub 2, and x sub 1. So, using back substitution, the quotient of 70 and 10. So, we have the value of 7. For our x sub 2, the difference of the product multiplied by the resultant x sub 3 and divide it all by the coefficient at x sub 2, and we will be able to find x sub 3. For x sub 1, 7.85 minus the product of x sub 3 minus the product of x sub 2 divided by the constant or the coefficient of x sub 1. And we will be able to find the value of x sub 1, x sub 2, and x sub 3 respectively. So, for our next discussion, Cholesky decomposition. So, recall that symmetric matrix is one where A sub ij is equals to A sub ji for all I and j. In other words, the matrix of A is equals to the transpose matrix of A. So, such system occur commonly in both mathematical and engineering problem context. So, they offer computational advantages because only half the storage is needed, and in most cases, only half the computation time is required for their solution. One of the most popular approaches involved Cholesky decomposition. And Cholesky decomposition's algorithm is based on the fact that a symmetric matrix can be decomposed as in the matrix A is equals to lower triangular format and multiplied by the transpose. That is, the resulting triangular factors are the transpose of each other. So the terms can be multiplied out and set equal to each other. So the result can be expressed simply by recurrence relations. So for the kth row, and so in order to understand the Cholesky decomposition, for example, apply Cholesky decomposition to the symmetric matrix. It is said that symmetric matrix has an A sub ij is equals to A sub ji. We have here aij, aji, and for this A12 is equals to A21, and they have the value of 10. For A13 and A31, they have a value of 8. For A23 equal to A32, they have a value of 26. They have symmetric matrix. So, Cholesky decomposition can be applied. So, this is matrix form. So, for the solution, so first we will apply matrix A equals to the value. So, we have here the lower multiplied by the transpose of the lower. So, this is for our LU decomposition, which is also called the Doolittle or the Kraut decomposition. So, for our Cholesky, you will notice that the L here is composed of A00, BC0, DEF, and for transpose, ABD, and 0CE, and for 00F, so 00F. And applying product, so this is the result of the product of the matrix. So, we will be able to calculate or to find the values of the unknown. So, A, B, D, C, E, and F. After finding the values of the unknown, so we will now be able to equate or to use the equation A multiplied by X equals to B. And we're going to substitute A to the transpose of LT, and this will be the represented function, and then I'm just indicating the difference of the Cholesky to our LU decomposition. And A, B, C, D, E, F. So, this is the value of our A, B, C, D, E, F. And from this value, we will be able to find the values of Y. And this is from the right-hand vector B. And then, for our solution process, so we will be able now to find the value of Y based on this equation. So, this is simply represented as Y equals to B. So, we have the values of Y and Y sub 2. And then, lastly, so from that, the equation will be used now is the transpose L raised to T, X equals to Y. So we will now be able to find the value of x. So let's now try using Excel, applying Cholesky decomposition. So we're going to use Excel and applying Cholesky decomposition. So this is the matrix coefficient A, the variable x, and the right-hand side vector B. So Cholesky method, so we have here for our A, so simply copy. But class, you have to take note that Cholesky decomposition is only applied to symmetric matrix wherein there is a similar values, or simply A sub ij is equals to A sub ji. For a matrix coefficient A, so simply copy the matrix coefficient from the given problem. And for our matrix L, so simply A, so this is A, 0, 0, B, C, 0, D, E, F. And for our transpose, so simply A, B, D, so A, B, D. So we have here 0, C, E, 0, C, E. And for 0, 0, F, 0, 0, F. So this is our matrix. So this is the composition of our matrices. So similarly, so let's simplify this. First, we'll copy the given for matrix A. So to be equated to the results of this particular multiplication of the lower and the transpose of the matrix. So let's have here for our first element. So the final result for first element is A squared. So this will be AB. So you just apply the basic rule of our matrices. This is AB, B squared plus C squared. And this will be BD plus CE. This will be AD. This will be BD plus EC. So this will be D squared plus E squared plus F squared. So you will notice the similarity or the symmetry of our matrices. So continuation of the solution process. So we have here A squared. The value of A squared is equals to 4, and A is equal to the square root of 4. So we already have the value of A. For AB, so AB is equated with a value of 10. And the value of B is simply equal to 10 divided by the value of A. So this is 10 divided by the value of A, and the value of B is 5. And for the value of AD, so AD is equals to 8. And for the value of D, so it will be equal to 8 divided by the value of A as 2. So this is simply 8 divided by the value of A, 2. So we have the value of D, and B squared, C squared is equals to 26. So we didn't recalculate this value and this value because they will have same result as this one because they are symmetric. So we're going to find the values of these three remaining equations. So now, so B squared is simply 5 squared plus C squared, which is the unknown, which will be equal to the value of 26. So C would simply be equal to, so 26 minus 5 squared, and this should be square root. And we will be able to find the value of C, which is equal to 1. And for our next one, so BD plus E plus CD is simply equal to 26. So we have the value of B, 5. So multiplied by the value of D, which is 4, plus the value of C, which is 1. So we will have here the unknown E and equated to 6. So E is simply equal to the value of 26 minus the value of B times the value of D. And we don't need to divide because the value of C is simply equal to 1. So we will be able to find the value of E equal to 6. And next, the last one, so finding the unknown or finding the value of F. So we have here 4 raised to 2 plus 6 raised to 2. So this is simply the value of D, the value of E, and the unknown is F squared. So equated to 61. So the value of F is 61, but don't forget the square root because we have here F squared. So 61 minus the value of D squared minus the value of E squared. And we have here the value of F as 3. So after that, so we have here first the problem equated to B. And then from our function, so we have here the value of A equals to. So substituting the value of A. So let's say that this is simply this particular equation multiplied by x equated to B. And let's say y is equals to the transpose of L multiplied by x. So therefore, we can simply say that L multiplied by y is equals to B. So first, we will have here the L. This will be the L. And this will be the transpose of L. So A, the value of A is simply A. So the value of B, the value of C, the value of D, the value of E, the value of F. And we have here the value which is 0. And for our transpose, so this is simply 2, 0, 0, 5, 1, 0, 4. So this will be the L and L transpose. So now we were going to apply this equation. Using this equation, so using the values at L for matrix L, and we will be able to find here the unknowns y sub 1, y sub 2, and y sub 3, and the right hand side vector. So from the problem, so this will be the process. And from this equation, so I'm not going to rewrite the equation anymore. So there is a similarity to the LU decomposition. So we will be able to find the value of y sub 1, y sub 2, and y sub 3. And this is using the back substitution. So we have here for y1, so we have the value of 44 divided by 2. For our y sub 2, 128 minus the coefficient of y1 plus y1. So, divided by the coefficient at y2. So, you will be able to find the value of y sub 2. For y3, so this is simply 214 minus y1, the coefficient multiplied. So, minus again for the coefficient multiplied by y2 and divided by 3. And you will be able to find the value of y sub 1, y sub 2, and y sub 3. And this will be used when finding the value of x. So, we will now be using the value of y. Using the transpose. And the value of transpose is 254. 25401. So, this is simply the transpose of this L value. And we will be able to find the value of x sub 1, x sub 2, x sub 3. And using y, so the calculated y value. So from here, we will be able to find the value of x sub 3, x sub 2, and x sub 1. So we have here 6 divided by 3. So we will be able to find the value of x sub 3 for our x sub 2. So this is simply 18 minus the coefficient of x sub 3 multiplied by 3. So divided by the coefficient which is 1. So we have here the value 6. So for our x sub 1, so this is simply 22 minus the product of coefficient at x sub 3 times the value of x sub 3 minus product of x sub 2. So coefficient of x sub 2 times x sub 2 divided by the coefficient of x sub 1, and we will be able to find the value of x sub 1. So therefore, this is how we use Excel in applying Cholesky decomposition and finding the values of x sub 3, x sub 2, and x sub 1.